Now, when the force vector acts perpendicular to the velocity vector, which it must do in a magnetic field, we have centrifugal motion, just like an orbit. And so basically any particle in a magnetic field is going to tend to want to move in a circle. So here I would say that the force directed into the circle is our magnetic force, and here is our velocity vector, so we're going to go in a circle. So, what is the radius of our circle? Might be one important question to ask, and we can get the radius from applying Newton's second law. We know the force is equal to our magnetic force is equal to m, and it's a centrifugal force, so we're going to use AC. We know force is equal to QVB, assuming that everything is perpendicular, so I'm just using the sign of 90 degrees here, is equal to m, and we're interested in the velocity is v squared over r. One of those v's will cancel on each side, so we get r is equal to mv over qb as the radius of that circle. So we can see that r is proportional to the momentum. Remember, momentum is mv of the particle, and inversely proportional to the magnetic field. So this is sometimes called the cyclotron equation because this is what we use in cyclotrons. Cyclotrons are big circles. And so we also might ask, what is the period of this particular motion? Remember, period is distance over speed. So if we take the circumference as the distance traveled, we can figure out what the period is of a particle traveling in this circle in this magnetic field. So now we're going to look at a use for some of these equations. We have here a mass spectrometer that has a singly charged carbon-12 atom moving in a magnetic field, and so it's going to tend to want to bend the direction of that particular particle. So it's being accelerated through potential difference. So this is an electric field type idea that the change in energy is equal to Q delta V. As a singly charged carbon moves in a radius, so this is the radius of motion, is 0.21 meters. What is the magnitude of the magnetic field inside this instrument? So we're going to use our force equation again. So force is equal to MAC, but this time I'm going to solve it for B because that is my unknown I'm being asked for. So that means V must equal to mv over qr. Now we know m, we know q, we know r, because m is the mass of our carbon ion, which is 12 times the mass of a helium ion. And so we can figure that one out. We just don't know V. So how are we going to get V? Well, we're going to use an energy balance. Kinetic energy final plus U final is equal to kinetic energy initial plus U initial. Presumably it started out with zero kinetic energy because it was accelerated through that potential difference, and it ends up with zero energy. So then we have kinetic energy final is equal to U initial, and that's 1/2 mv squared is equal to qv, where this is volts and this is velocity. And then we can solve for our velocity is equal to the square root of 2qv over m, and we know all those values, so we can get the square root of 2 times 1.6 times 10 to the negative 19th coulombs times the 5 times 10 to the third volts, all over the mass is 12 times 1.7 times 10 to the negative 27th kilograms. And we take the square root of all of that, and we get the velocity is 2.8 times 10 to the 5th meters per second. Now we can use that in our equation for B is equal to mv over qr. So m is again 12 times 1.7 times 10 to the negative 27 kilograms times that velocity we just found, 10 to the 5th meters per second, all over 1.6 times 10 to the negative 19th coulombs times 0.21 meters gives me a magnetic field of 0.17 Tesla. And we could have done that a different way. We could have taken our V equation and plugged it directly in, done some cancellation, and overall plugged fewer numbers in the calculator to get exactly the same value. So where is this idea used? Well, this is how we accelerate electrons and protons in a acceleration chamber such as Fermilab in Batavia, Illinois, and at CERN in Switzerland is currently the collider that they're using. And what happens in these colliders is they actually collide two protons and are able to basically create enough energy that they're able to get energy to recondense into particles. So these are not particles that are involved in the proton at all. They're creating particles out of the energy using E equals mc squared. Now, the smaller version is actually used sometimes in a hospital. This is called a cyclotron, and both of them are called a cyclotron, but they come in the one that are multiple miles across, or they come in basically desktop versions. Cyclotrons are used in production of radioactive nuclei such as technetium, and also used in proton beam therapy. So these would fit on a desk or in a room. Both are called cyclotrons. And here the electric field in between these two halves are what accelerates it, and then we use the magnetic field to get the protons to come back around. And each one of these things is called a D because they look like a D. Now cyclotrons, like we said, are used for making radioactive materials. So what happens is you take molybdenum and you shoot a proton at it, and it becomes technetium. Cyclotrons then use it to bind to calcium and look at blood flow. And so if you're doing radioactive studies in a hospital, technetium is very popular because you can pick it up on an MRI machine. Now, the charged particles within the magnetosphere of the Earth also move in these circles as they radiate into Earth, and this is why we get northern lights, is these charged particles enter the atmosphere at the north and south pole. We also use these in mass specs. Mass specs don't travel in a complete circle, but we use these to bend particles based on their mass. The typical units on one of these charts is mass over Z, where Z is the charge. So what it's measuring is the mass to charge ratio because of the equation. Is we said R is equal to mv over QB, so we can control the velocity things come in at, we can control the magnetic field, and then what's left to tell us what the species is the mass divided by the charge, and typically most species are singly charged. So if we assume that each ion is singly charged, what is going to be basically the order? What, if you run a mass spec, which one will land farthest from the detector? Now the detector is typically at an angle up here because we just have a small area of magnetic field, so we get a small amount of bending in the path. But in principle, we're going to talk about this being the radius because we're going to talk about the path coming all the way back around, so we could talk about the radius of travel. So which one's going to be bent the most or land farthest from the detector? Well, the answer is, of course, CO2 because it has the highest mass, and you can see that over here on the graph that it has the farthest away peak because it has the highest ratio of mass to charge.